So back here with our second video discussing continuity and talking about how to prove if a function is continuous or is it continuous at a particular point. So I have over here the same little definition that we came up with last time, the three conditions we need to meet in order to prove that a function is continuous at a particular point. Now, if we want to say that the function is continuous everywhere, then we would have to show this definition for every point along the graph, which is a lot. So typically what we end up looking at and what you will be asked to prove in AP Calculus is continuity at a particular point. Now, there are some functions, our parent functions, if you remember, that we can just go ahead and assume, and we know already that it is in fact continuous. So those types of functions are your polynomials. Those are always going to be continuous. So these are continuous functions. So these are kind of like what you can consider your default. We don't have to prove it. We know it's true. We've been familiar with the graph. We've worked with it for years. There no need to check that they are continuous. It is. So polynomials, so your quadratics, cubic functions, etc., etc. We know those are continuous functions. Some of our trig functions, so particularly sine and cosine, are continuous functions. Notice I'm not saying all trig functions because we know tangent, the reciprocal functions, they have asymptotes, so that's a no. So these are also going to be continuous functions. Your exponential function is a continuous function. I don't say log. Log has a vertical asymptote, so we're not covering everything. Exponential functions are also continuous functions as well. All right, so we're going to take our first example here. Now we have a piecewise function. Now usually these are the ones where when we get these given to us, because of the nature of a piecewise function, we're not sure, unless we actually graph it, we're not sure right out of the gate, is this a continuous function? There might be parts to it that, there's a jump or the two pieces don't connect. So we want to check this here and prove, is this function, is f of x continuous at 1? That's the question, because that's where the break is happening. So I see that this branch of the function is a continuous function because it's a polynomial. This branch of the piecewise function is also a polynomial. So that is a continuous function. So the two parts are continuous. But the question is, do the two parts connect? Because it might have a gap. Maybe it looks something weird like, this. Or maybe something like that's happening. That would not be a continuous function. So we can't just automatically stare at the parts and just say, well, all the pieces are continuous, therefore this thing's continuous. Do the pieces connect? That's the question. So that means we're going to run through our definition. So the first part is, does f of 1 exist? Do we get an answer for f of 1? So according to the piecewise function, if we plug in 1, that would fall under this condition. 1 squared is 1. So yes, that first part, we're checked off. So f of 1 exists. Next, does the limit as x approaches 1 exist? Okay, this is a piecewise function. I can't just plug in the number because I don't know if it's continuous. That's the only way. We cannot do a direct substitution. I have to do, which is what we did in assignment number 1, is those left and right hand limits. So in order for me to answer this, I'm going to have to do a little side investigation. So what's the limit as x approaches 1 from the left? So numbers less than 1. Well, if we're less than 1, we're using this top branch here, and we would be approaching 1. So you can confirm that by doing it numerically, doing it graphically. This, and this is why I said earlier, this already I know, this part of the piecewise function is continuous. Therefore, I can directly substitute in there. So I know that this would become 1. So as I approach 1 from the left, it is approaching 1. What about if I approach 1 from the right? So if we're approaching 1 from the right, numbers bigger than 1, then we're using this function. And again, this I already know is continuous, so I could directly substitute, and I get 1 as well. So both the left and the right hand limit are the same number. Therefore, yes, the limit exists, and the answer is 1. That's checked off. So now we have to do the final condition, which is again our kind of, I like to call it the concluding condition, which is, do these two parts, are they giving me the same value? And the answer is yes, they are. So limit as x approaches 1 of f of x is equal to f of 1. So yes, we do meet that condition. So all 3 conditions have been met. So now I can conclude, therefore, f of x is continuous at x equals. This, all this work that I did here, is our proof. This is our justification to show that yes, in fact, this function is continuous at this particular value. Now, if we wanted to prove continuity at a different point, we'd go through this whole process all over again. So I could now generalize even further and say this is continuous for all values of x because of the fact that I already know these 2 pieces are continuous. So since x is continuous for all values less than 1, I know x squared is continuous for all values greater than or equal to 1 because they're polynomials. And we just finished checking the critical part, the shaky part, which was the part where it's disconnected, but we see even though it's jumping to a different function, those 2 pieces actually connect. So therefore, I can even go one step further and say, not only is this continuous at x equals 1, it's continuous for all values of x. We cannot do that all the time. So if I had this function up here, and if it was not continuous, then I would have to discuss, hey, you got a problem here. So as an example, let's take this same exact setup, and I'm going to actually change it up by saying this up here is 1 over x, and this is x squared. So if this were f of x, and I asked exactly the same question as I did over here, is it continuous at 1? The answer is yeah, it will be, because all 3 of these would be fine. However, could I say it's continuous for all values of x? Is it continuous for any value of x? No, because this branch of the piecewise function is not continuous. There is a value that will cause this to break, and that is going to be when x is 0. And that actually falls under its domain. Because if I did have 0, I would have to go through this function, and it's not going to be continuous at that part. If we graphed it, we would see that it actually does show us, because we would be seeing something. So let me sketch the axes. So I would be seeing something like this. Whoops. I would see something. So let's say, so here's at 1. So I'm going to draw like a little dotted line here to indicate this is at 1. Okay. So here's where the reciprocal function stops, and then the parabola would have picked up from here. So you can see this would be the graph of this f of x, but it's not continuous because boom, right there's that asymptote. So I cannot say, is this continuous for all values of x? No, because this branch I already know is not continuous, and it's going to show its discontinuity because 0 is going to be included. So just an example of, just because we prove continuity at a point doesn't mean it's continuous everywhere. So now let's go ahead and we'll do one more example. And actually, I'm going to save my next example for another video, just because we're hitting the 10-minute mark here. So again, there's our definition, and we did an example of going through and proving continuity at a particular point.